During the Big Bang explosion, the whole universe blew up essentially and expanded very rapidly. So the cosmic matter web contains all of the original matter that was created during the Big Bang, just blown up into the very, very large structures that we see today. The cosmic matter web is not actually the largest gravitationally bound object in the universe, because all the matter in the universe has expanded so vastly, the force of gravity is not enough to keep it together in one area, whereas superclusters of galaxies are actually gravitationally bound, meaning that they have enough mass to produce enough gravity to hold them together over the passage of time. I have here a small toy boat, which is a replica of the Queen Mary, which you can see here behind me. And this little toy is about 4,000 times smaller than the real Queen Mary. If you could just imagine that our own Milky Way galaxy that we live in is the same size as this toy boat, then one of the most massive superclusters that we know about, the Shapley supercluster, would be the same size as the Queen Mary. So this Shapley supercluster would be about 4,000 times larger than our own Milky Way. It's one of the most massive things we know about in the entire universe. As the universe evolves and expands, gravity is an attractive force, so any region that has a little extra density there attracts more matter and more matter. So Shapley is a cluster that basically had the accumulation of many other little galaxies falling into it, and that's how it's gotten so big over time.
Incredibly, scientists think the Shapley supercluster may be even bigger than it appears.
In fact, we may only be seeing a small fraction of what's really contained within the Shapley supercluster. When the Wide Field Infrared Survey Explorer launches, we should be able to see about 10 times farther away, and hopefully we'll be able to see the rest of the Shapley supercluster to see if it is even more massive than what we already know about.
Superclusters of galaxies will stay together over time because they're gravitationally bound.
Gravity is holding them together, so even though the universe is expanding, over time, those superclusters of galaxies will stay together, and they'll always keep orbiting each other. When we're looking at the Lyman alpha blob, we're seeing gas that's sort of spread amongst these very first stars and galaxies. It's kind of an amorphous shape of about 30 separate little blobs inside of it. It's very large and very massive. The whole structure is about 3,000 times the size of our own Milky Way galaxy.
However, there are other objects even larger. They're called radiolobes. Stretching out from both sides of a galaxy, these immense structures are actually hurling jets of charged particles that emit radio waves.
So we're here in this auto body shop where I'm going to use these two torches to simulate radio jets coming out of opposite sides of an accretion disk swirling around a supermassive black hole. So in the visible, you see a small blue flame coming off of the torch, but in the infrared, you can see that the heat from the torch extends much, much further out. Similarly, with the radio jets, what you see in the optical is actually quite different from what you see in radio waves. So just as this torch will eventually run out of gas and shut itself off, the jets from a radio galaxy will eventually die as well. When the black hole has consumed all of the material in its immediate vicinity, there'll be nothing left of the accretion disk to get shot out along the magnetic field lines, and the jet will die. The center of our Milky Way, we know that there's a black hole that's about maybe 3 million times the mass of our own sun. And yet, because black holes are so incredibly dense, the actual size of the black hole is still fairly small, but incredibly, incredibly powerful gravitationally. Now, that assumes that you can measure its luminosity fairly well and that you know something about its temperature from its color. Most of the time, they just simply appear as pinpoints of light, and it's impossible to actually resolve it. Although there are new instruments now called interferometers, which are capable of resolving even very tiny point sources, like stars. And in some cases, there have been direct measurements of stellar diameters. Trace 4 is unusually large for its mass. We can actually directly measure its radius, and this particular planet has an unusually large radius. It's about 70% bigger than Jupiter, yet it has only about 80% of Jupiter's mass. That's about the same density as quark or even whipped cream. This particular planet is only about 5% of the Earth's sun distance from its parent star, so it's very, very close. In fact, so close, it orbits its star every 3.5 days. So you can imagine how hot and how just blasted with sunlight this thing must be. Because the planet can't cool off, it can't shrink. Because when it's very hot, when gases are very hot, they expand. So this might be contributing to keeping the radius of this planet so very large. This planet would not be a very habitable place because it's so close to its parent star. It's getting blasted with radiation from its sun. So it would be a very hot and unpleasant place to be, at least for humans. Scientists are finding new planets basically every day almost at this point. So it's quite possible that we will find another one that's even bigger than this particular planet any time. The current definition of a dwarf planet is something that in fact is massive enough and has enough self-gravity to form itself into a round shape. And in fact, since Ceres is round, we also call it, in addition to being an asteroid, a dwarf planet. We know only a little bit about the composition of Ceres right now. We know that it's made primarily of rock, but it may also have water ice, and in fact it could have clay inside it as well. The Dawn mission is actually going to go to Ceres and enter into orbit around it, and they'll bring a whole suite of instruments to bear on it, so we should learn a lot more about the composition of this unusually large asteroid in our own solar system. It's quite possible that as we go on to exploring other solar systems outside of our own, that we may in fact someday find an asteroid larger than Ceres.
Our solar system contains some oversized objects. The largest planet, Jupiter, has the biggest moon, named Ganymede. Planet Mars actually contains the largest volcano, called Olympus Mons.
It's 17 miles tall, which makes it about 3 times taller than the biggest volcano we have on Earth. It's so tall that if you stood at the base of Olympus Mons, you wouldn't be able to see the top due to the curvature of Mars itself. So in our own solar system, the biggest things definitely have had a powerful shaping effect on the universe.
The origins of the Oort cloud remain puzzling. One theory is that it was formed early in our solar system. As comets fell in towards the forming sun, they were ejected into long orbits. Over time, their orbits threw them out into a giant cloud.
It's very far away, and it's filled with icy remnants that have just been left in basically the same state that they were from right around the time when our solar system formed, about 4.5 billion years ago. So they are, you could say, the archaeological remnants of the formation of our solar system. Astronomers are hoping to find new large planets, new huge superclusters, and learn more about the things that we've already seen. As technology improves with better telescopes, better detectors, newer surveys, we will be able to see farther into space and therefore hopefully discover even bigger things than we already know about.